Testing, testing. Today I'd like to follow up on the proof of Fermat's little theorem, not his big theorem because that's about 600 pages. The xn plus yn equals en has no solutions for positive integers n bigger than 2. The proof of the Fermat's little theorem says that if p is a prime number and a is a natural number, then a raised to the power p equals a mod p. That means if you divide p into a raised to the power p, you'll get the remainder a. So I'll show you how that actually works, and then we'll talk a little bit about where some of these interesting problems may come from. Okay, so I want to talk today, just go through a proof or an outline of the proof of Fermat's little theorem. And underscore the word little. So what I want to do is show if p is a prime and a is less than p, then a mod, or a to the p raised to the power p equals a mod p. Okay, so this is just an induction. Actually, this part holds true for any two numbers here, so I'll get back to that. So if it's true for a, then we want to check and hold that it holds true for a plus 1. You can verify that it holds for a small integer. So what we're going to do is just consider this quantity, a to the p plus 1. No, excuse me. Jumping ahead, I have to do a plus 1, not a to the p plus 1. So I'm going to look at a plus 1 raised to the p plus 1 minus a plus 1. So I'll consider this quantity. And by the binomial theorem, or just the binomial expansion, I'm going to expand a plus 1 to this. So we're going to get a, again, and I don't want to put p plus 1, I just want to put p. Okay. So a plus 1 to the p. I'm replacing a by a plus 1 in this statement here. So a plus 1 raised to the p power clearly is equal to a to the p plus p times a to the p minus 1 plus p minus 1 over 2 factorial a to the p minus 2 plus etc. And the last term is going to be 1 raised to the p, which is 1. And in terms of the binomial coefficients, this is a p plus p1 a to the p minus 1 plus p2 a to the p minus 2 plus p. So these binomial coefficients, you'll remember, are given by nk equals n factorial, n minus k factorial, k factorial. So these are just permutations, combinations, etc. Now do notice, for example, that all these factors here are divisible by p, since they contain p as a factor, except for the first one and possibly the last one. Okay, so this is p is divisible by p. P times p minus 1 over 2 is divisible by p. The third one is p times p minus 1 times p minus 2 divided by 3 factorial. Obviously, they're all divisible by p. So p k, which is p factorial over k factorial, p minus k factorial, is divisible by p if k is not equal to 0 or p. Okay, because it contains p as a divisor. Okay, so let's just go ahead and subtract. So this implies what? This implies that a plus 1 raised to the p minus the two terms that are not divisible by p. Excuse me, that should be a minus 1. If you look back on that, that's equal to a plus 1 raised to the power p minus a to the p minus 1 is p over 1, or the binomial coefficient p1, a to the p minus 1. Oops, did I? So a to the plus 1 raised to the p minus a to the p minus 1 is equal to p over 1, a to the p minus 1, plus p over 2, or p choose 2, a to the p minus 2, plus, etc., p choose p minus 1, a times 1. Okay, so each of these is divisible by p, so a plus 1 p minus a to the p minus 1 equals 0 mod p. So all of these terms contain a factor, at least one factor of p. Now, by assumption, a p minus a equals 0 mod p, because AP is equal to A mod P. So AP equals A mod P implies that A sub P to the P power is a multiple of P plus A, right? So that implies that A to the power P minus A is a multiple of P, so therefore mod P is 0. Okay. So if this is divisible by P, and this left term here is divisible by P, I can add the two. So add the two expressions. So I'll call this star and double star. Add these two expressions together, and what do we have? We have A raised to the power P plus, sorry, keep writing that. A plus 1 to the P power minus A to the P power minus 1 plus AP minus A equals 0 mod P. Since this term is divisible by P, as is this, P is a common factor to both, but notice that this cancels with that, and so therefore A plus 1 to the P minus A plus 1 equals 0 mod P. Okay, so that is a proof that this is true. AP equals A mod P. Okay. And as we mentioned before, this is used as a test. For primality. So if the theorem is that P is a prime, implies that AP equals A mod P, then if A, P is not equal to A mod P, what can we conclude? If A implies B, then not B implies not A, right? That's the converse. So P is not prime. So if you take a number, P, and you divide it by a number A, and if you take, so given integers P and A less than P, if you take A to the P power and you divide it by P, and it's not equal to A as a remainder, this implies P is not prime. So this is a very simple test to say if a number is not prime. Unfortunately, it's not a test to show that it's prime, because it's not if and only if. If it were if and only if, it would say A raised to the P power equals A mod P would show that P is a prime, and that's not true. So there are numbers, unfortunately, there are composite numbers, non-primes. So there are non-primes with AP equals A mod P for all A less than P. And the number of P equals 561 is the first such occurrence. And these are called pseudo-primes. And they're relatively rare. And a lot of tests for primality have to do with randomly picking numbers A less than P, performing this division, A raised to the P power, dividing it by P, seeing what the remainder is, and checking it. So obviously, when you're in the binary system, dividing numbers by P or so is fairly efficient. Okay, so these pseudo-primes are what mess you up. So if you could eliminate all the pseudo-primes, then you'd be in good shape. So it was thought for a long time, it was thought that you could generate primes by some formula. So for example, there's a formula that generates quite a few primes. Let's see if I can. So for example, the following formula, P of x equals x squared plus x plus 41 generates primes for a certain range of integers, x equals 0 up to 40. But after 40, it's no longer prime. So afterwards, it sort of produces primes half the time, and for beyond 10,000, the number of primes decreases. So for x being bigger than 10,000, less than half are primes. So someone said, well, maybe we just need a bigger polynomial formula. X squared plus x plus 17 generates primes up to 0 to 15, but in general, no polynomial formula can generate only prime values. Now, people have graphed primes and tried to find statistical properties of primes. Another type of prime number is called the Mersenne primes. So Mersenne numbers is a number which is 2, this is m sub p, it's 2 to the p minus 1, and this is often a prime. So for example, the 7th Mersenne number happens to be a prime. And in fact, the first primes, it's prime for the following numbers. P equals 2, 3, 5, 7, 13, 17, and 19. It's not prime for 11. So m sub 11, which is 2 to the 11 minus 1, is actually equal to, and you can just compute it, is 2047. And that's actually a composite number, 23 times 89. So it's not true, it's missing the number 11 in here. Now, people have actually found Mersenne primes for very large values of p. The number 2 raised to the 21,701 minus 1 is in fact a prime. And it's the 25th Mersenne prime, and it contains 6,533 digits. Okay. Another way of generating primes that was early thought is to multiply the first n primes together and add 1. So suppose I have the first prime times the second, third, up to n primes, and then I take that plus 1. So if I multiply all the primes together, is this prime? Well, the results look promising, but it turns out that no, it's not true. So let me just show you the first. So as an example, if you take 2 plus 1, that's 3, that's a prime. 2 times 3, the product of the first 2 primes plus 1 is 7, which is a prime. 2 times 3 times 5, the first 3 primes plus 1 is 31, which is a prime. And in fact, it looks good up to 11, but if you do it for 13, 3 times 5 times 7 times 11 times 13 minus 1, this is 30,031, and that's unfortunately composite. So that's 59 times 509. So the point is no matter how promising the sequence of primes, it's very difficult to generate a sequence of only primes. So generating primes is tough. So generating primes is hard. It's an unsolved problem. We don't know if it's unsolvable, but it's unsolved. How do you generate primes? Factoring composite numbers, large composite numbers, is very hard, although not as hard as this. It is hard, although it's not unsolved, it just takes a long time. Particularly when the composite number is the product of 2 primes, P1 and P2, where P1 is approximately equal to P2. If you have a composite number, say of 512 digits, and it's the product of 2 primes with roughly 256 digits, it's very, very, very complicated and expensive to factor. Okay. What we have seen, though, is it's easy to determine if a number is not a prime. If a number is not a prime, just by that a to the p equals a mod p test. Okay, but this does not give you factors, and furthermore, it's not foolproof. You can get numbers which satisfy this, which are not prime. So all of these together, essentially, the difficulty is what underlies are good, because the difficulties ensure the difficulty of code breaking. Okay, and maybe next lecture we'll talk a little bit about not the RSA encryption algorithm, because someone's doing that as a project, but a general code breaking in particular. Now, I did want to talk a little bit about the following. We've talked in this course about a number of kinds of mathematical problems. So as we've seen, we've had historical problems from ancient Mesopotamian, Egyptian, and Greek mathematics. We then talked about the axiomatic systems and how they generated primes and the difficulty with purely axiomatic systems. We then took a little foray into the beginnings of analysis as limits and functions. We then sort of combined analysis with geometry and applications, and then moved into a very popular area called calculus of variations. Now, as you can see just from briefly glancing through this list, that mathematical problems come from many different types of areas, and the kinds that we've covered in this course include the following. You can have more or less pure math. Now, as we saw, the natural numbers can essentially be reduced to axiomatic set theory. So axiomatic set theory essentially generates the natural numbers, and factoring and prime numbers and composites and etc. can be just determined as properties of natural numbers and their factors. But it is known that axiomatic set theory is not a complete system because of Gödel's result. So Gödel's result in completeness theorem, there are statements which cannot be determined whether they're true or false. Now, because number theory is tied in with the properties of natural numbers and hence set theory, it's very possible that you can make a statement in number theory which cannot be proven just based on properties of the natural numbers alone. So it's possible that there are results in number theory which cannot be proven by just the elementary properties of numbers. Natural numbers. And many people actually believe that some of the results about prime numbers fall into this. In other words, trying to determine whether there's an algorithm to factor large composite numbers, the existence of an algorithm may not be able to be proved or disproved. An algorithm may exist or an algorithm may not exist, but we may not know unless you could actually stumble upon it. So some mathematicians actually believe that some of the open problems in number theory are essentially not provable or disprovable, just assuming the elementary properties of numbers and factoring numbers and results that we now have in number theory. For example, statistical properties of the distribution of primes might be one of these, unknowable. Can you deduce a statistical distribution which governs asymptotically the distribution of primes? That might be, again, one of those non-knowable. So when you have a pure axiomatic system, you essentially lay yourself open to the possibility that you can be asking a question that is essentially not provable or disprovable based on the properties and systems that you write down. Now, there are also open problems that come from descriptions, more or less the applied world. So there are problems, let's get a new page here. So there are problems that come from non-pure areas. Applied areas. And these are more or less the problems, for example, when you look at the problems that are the million-dollar problems from the Clay Institute. So we'll do the unsolved problems. These are more or less problems which come from some of the more applied areas of mathematics. For example, the Navier-Stokes equations and their existence for large velocities and large time. The Riemann hypothesis, that's more or less a pure. Yang-Mills theory, Hodge conjecture, etc. Some of these come out of theoretical physics, etc. So these kinds of problems do stand a chance, since they don't come from axiomatic systems. So the existence of Navier-Stokes, Yang-Mills, etc. These can be essentially, possibly be determined, since you're not really formulating Navier-Stokes as an axiomatic theory. Although one could argue that continuum mechanics is axiomatic, but the existence to the solutions as partial differential equations doesn't really come from an axiomatic theory itself. So applied areas generate non-axiomatic systems. And hence may not be, or possibly could be, subject to Gödel's incompleteness. Now, modern theoretical physics, and this was the talk of Stephen Hawking not too long ago, is essentially an attempt to reduce physics to an axiomatic system. Physics to an axiomatic system. So essentially you postulate an underlying PDE, like the Einstein field equations, and then you postulate certain behavior. You postulate that the universe does not contain a boundary. You don't necessarily say that it's infinite or not infinite. You postulate certain conservation laws and things like that, and then based on those assumptions, you try to determine the behavior of the universe. But again, there are some unknowable questions, like how did the universe begin, or is that in fact a meaningful question? Is there a time t less than 0? Can you continue the universe backwards through its starting point? Or does it sort of periodically cycle, or does it have a beginning or an end? Or modern physics actually looks at a four-dimensional. In 3 dimensions, you can talk about sort of a t equals 0 and in the universe as t goes to infinity, but if you look in the complex plane, then in fact it's embedded in a geometry of complex space and complex time where the universe doesn't in fact have a beginning or an end. So that's sort of the modern conception. Okay. But the prime numbers are coming from a very pure, very axiomatic system, not natural numbers, which essentially comes from set theory And it is known that there are results coming from set theory that are not determinable. Okay, so I think that pretty much finishes what I want to talk about on the proof of Fermat's Little theorem. And I think next time I'll probably wrap this up, the next lecture on encryption in general, to sort of the main ideas of public key, public and private key encryption. Because it's not the details, but just the idea. So I'm going to talk about the ideas underlying public and private key encryption, in particular the PGP. So it's a pretty good public key encryption algorithm. And this is built into Unix or Linux. Okay, and then we'll possibly work more on our